Okay, Math 5130. This is probably, I can't think of anything else I'm going to throw at you. Probably the last video of Lesson 7, the last video of the term. So, yeehaw, right? The one we've been waiting on. This is a doozy though, so we're gonna go out on a bang. So, let me regroup here a little bit. Okay. The purpose of this video is to help you learn how to make predictions with a logistic regression model. So I'm going to kind of bounce it off what I have over in the left side with R. So let's just say, for example, I'm using logistic regression 2 data set. And let's just say, for example, that we want to predict falls from age, upgo, and feel. So I did the standard stuff in terms of forcing falls as a factor, renaming it for something just easier to type, and releveling so the reference category is clear. So ran my model, got my coefficients. Now, let's put this in the context of something we should be able to do very easily. Back in lesson 6, when we got into multiple regression models, we had a model where we predicted SSQ and we got the following coefficients. So since SSQ is quantitative, predicting SSQ, just for example, when we have a patient with an age of 55, and an HFSSI score of 53, it'd be very easy. We just insert 55 into our model, insert 53 into our model, do the arithmetic, and we get our prediction, 90.81, done, easy peasy, right? Not so much with logistic regression. With logistic regression, much more complicated. So the model I have calculated over to the left says that we can predict falls. And remember, 1 is reported as a fall and 0 is reported as not fall, right? So I have the coefficients 2.978, 0.354, 0.051, negative 1.264 that I get from my model. All right, so just put those in. So if I want to find the probability of falling when, for example, the age is 76, the upgo test is 11, feel is 4.3, I just chose these numbers as an example. Nothing, holy about this particular subject who's 76 years old with just an example. It's easy for me to calculate the right-hand side. And the right-hand side is just calculated by inserting the 76, the 11, and the 4.3 into the coefficients that correspond with age, upgo, and feel. So I get down to 0.295, and what does that represent? Well, unfortunately, in the logistic regression setting, it doesn't represent something as easy to understand as it does in the multiple regression setting. So what this represents, if we just now focus on the left-hand side, the predicted falls when, again, the reference category is not falling, is actually the natural log of the odds of falling. And remember that the odds are nothing more than the probability divided by with probability of something falling. In this case, it's the probability of falling over the probability of not falling. So we take the natural log of the odds, which again is this probability, divided by 1 minus the probability. So I know from my right-hand side, which I've calculated to be 0.295 from the previous page, right, that the natural log of the odds is equal to this value. I do some trickery next. I exponentiate both sides. So I take base E and raise the left-hand side to that power. And I take base E and raise to the power of 0.2952. There's a fancy schmancy little property that says if I take E raised to the natural log of something, it's just that something. So if I take e to the natural log of something, p over 1 minus p, it's just that something, p over 1 minus p. And if I plug this in my calculator, I get 0.2952 e raised to that power. Turns out it's just 1.3434. Now, let me demonstrate to you in my calculator. So I just took e raised to the 0.2952, and you can see that I get the 1.3434. All right. So the next thing I have to do is I set this equal to this as that, and then I cross multiply. So I have p equal to 1.3434 times 1 minus p. Distribute the 1.3434 through to get p equal 1.3434 minus 1.3434p. I add 1.3434p to both sides. Remember, this is 1p. So 1p plus 1.3434p is 2.3434p equal what's left over there. Do the division, 0.573. So the probability of this person, let's go back to this person. This person who is 76 years old, has an UPGO test of 11 and a feeling score of 4.3, the probability of them falling is 0.573. Now, let's think about this in the context of, well, okay, let me go ahead again. So the probability of this person falling is 0.573, so the probability of not falling, let me try to make this a little clear, that bugs me. So the probability of not falling would just be 1 minus the 0.573 or 0.427. Now, let's see how this works if we have a data set. Now, a lot of times, namely my stat lab, you will have a situation where you are just, let me go to, okay. You'll have a situation where you don't have your data, but you just have your regression model. And then you just follow this to get that. But sometimes you get in a situation where you have your data set, you calculate your model, and you can use R to get these values. For example, now that I have my, my model created, I can just do fitted model, and let's look what pops up. For the first case, 0.518. How we get that? Well, the first case has an age of 73, which I put into my model. They have an UPGO score of 9.97, which I put into my model. And they have a feel score of 6.5, which I put into my model. I calculated the right-hand side as I did previously. I get 0.0717. That's the natural log of the odds. Exponentiate both sides. So I have that the odds are equal to 1.0743. Change it to probability over the not probability. Do the math. Well, it's not even really math, it's arithmetic, and I get 0.518. Something else that I think is kind of cool is I can do not the see what is that to get the oh shoot, yeah, here we go, predict model. And notice that I get, when I run the predict model, I get the 0.0732. Does that look familiar? Yeah, that's exactly what we get right here, within some degree of rounding. So finding probabilities are super easy to find if you have the data set and you can run the model. I don't know how to do this in StatCrunch. I don't think, in fact, I don't think there's a way to do it in StatCrunch, but there could be. And finding the natural log of the odds is also easy to find. But this would be, if you're finding probability, the fitted model would be the value that corresponds to the probability of this person reporting a fall. And of course, the probability of them reporting a not fall would be 1 minus 0.518, which would be what, 0.482. So they would be easy to do, just subtract from 1. All right, gang. I mean, I could go on and on. I love teaching logistic regression, but we have to end it someplace, so let's do that.